Hi students. So hope you have all understood the previous video. Okay, in the previous video we learned about the NK linear block code, where N stands for the number of output bits and K stands for the number of input bits. Okay, and always the value of N is greater than the value of K. That is, the number of output bits is greater than the number of input bits. And also we learned that you can create the output code word from the input message by using the equation V is equal to U into G, where V is the n-bit output code word, U is the input message block, and G is what we call as the generator matrix, whose dimension is given by K by N. That is, it has K rows and N columns. Okay, this is what we learned in the last video. Now here you're going to learn another interesting topic, and that is the systematic block code. Okay, systematic block code is actually a type of NK linear block code, but it has some magic inside. It has some fantastic property inside. Just look what a systematic block code is. For an NK linear block code, if either the first K digits or the last K digits, that is, we know that the value of N is greater than K. Okay, so if either the first K digits or the last K digits of the output code word is the same as the message block, then we say that the code is a systematic block code. That is, we know that the value of N is greater than K, right? So the value of N is greater. So assume that this is the N-bit code word. Okay, if the n-bit code word, if the first part of the n-bit code word is exactly the same as the message, it can either be the first part or the last part. If the first part or the last part of the entire output code word, if one part of it is the same as the input message itself, then that code is what you call as the systematic block code. Okay, it is a type of NK linear block code. So if you look at this example here, this is the n-bit code word, and this n-bit code word, the first part is exactly the same as the input message, which is of K bits, and the remaining is the N minus K bits, is the redundant portion or the redundant block. Okay, see, the best way to explain this to you is by using the previous example. In the previous example, we have all learned with the example with the problem, right? There is a 6-3 linear block code, and you have all learned how to find the code words using the 6-3 block code from looking at the generator matrix. So I have just written the same table over here. Okay, the previous problem, same answer I have written once again over here, just so that you will understand what is a systematic block code. Okay. So here, this is a 6-3 linear. The previous example, the previous problem you did was the 6-3 linear block code, and in this previous example, N is equal to 6, K is equal to 3, which means the value of the output bits is 6, and the value of the input message is 3. So therefore, V1, V2, V3, V4, V5, V6, and U1, U2, U3. Okay, so this is the 6-3 block code. Now look at the first portion of the output code word, the first 3 bits. Here the input message is equal to the input message bits is equal to 3. So now look at the first 3 bits of your output code word. Okay, if you look over here, they both are exactly the same. That is, here also 0, 0, 0, here also 0, 0, 0, here 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1. See, so that means the first portion of your output code word is the same as your input message. This is what you call as the systematic block code. That is, the first or the last. It can be any one of them. It can either come at the first portion of the code word, or it can either come at the last portion of the code word. If any one of the part of the code word is exactly the same as your input message, then that code is what you call as an NK linear systematic block code. It is a linear block code, but it is also having a systematic structure in which a part of the code word is exactly the same as your input message itself. Okay, that is called as systematic block code. Now, how did this happen? What is the trick behind it? How did the first 3 letters became exactly the same as your input message? How did that happen? In order to do that, all you need to do is simply look at the generator matrix. That is where the trick is. This is the generator matrix of the previous problem that you did. using 6-3 blocker. This is exactly the same matrix I've written one more time. Okay, the trick lies over here. If you at starting, if you simply look from far away, you'll just see a bunch of ones and zeros all random, right? But if you look very carefully inside this matrix actually consists of two parts. Let me draw a line for you so you can understand. There. This generator matrix is having two parts. This is one part and this is the other part. Okay. This is also supposed to be 0, 0, 1. Yeah, this is the question. This is the generator matrix, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the generator matrix you did, right? So you look over here. This is the first part. This is the second part. Now, what is the first part looks like to you? The first part, that is this matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. You all know what this matrix is called. This matrix is actually called as nothing but the identity matrix. This is called as the identity matrix. Okay, and you all know what is an identity matrix, right? That is, identity matrix is actually a square matrix. Square matrix means always the number of rows will be equal to the number of columns. So it is a square matrix in which only the diagonal elements are 1 and the remaining elements are 0. That is called as an identity matrix. Okay, and any matrix multiplied by with the identity matrix is that matrix itself. That is one of the unique properties. It is just like saying if A is a matrix. Okay, if A is a matrix and then A into I is equal to A itself. That is the meaning of this. This matrix is actually called as I3. Okay, I3. This 3 stands for 3 rows and 3 columns. Always the number of rows is equal to number of columns. That is why this is also a square matrix. It is a square matrix. Identity matrices are all square matrices in which all the diagonal elements are 1 and the remaining elements are 0. And any matrix, that is one of the property you must have studied in school, right? When you learn about matrices, that is, any matrix multiplied with the identity matrix is that matrix itself. Okay, and this generator matrix has an identity matrix inside. That is why when you were actually multiplying U1, U2 and U3, right? When you were trying to find the value of V1, V2 and V3, when you were trying to find the value of V1, V2 and V3, what you were actually doing was you were actually multiplying U1, U2 and U3 with the columns of the identity matrix. This was being multiplied with U1, this was being multiplied with U2, and this was being multiplied with U3. That is why V1 is equal to U1, V2 is equal to U2 and V3 is equal to U3. That is why you got this same value as your message bits itself. The other portion, the remaining portion of this matrix is what you call as the parity generator matrix. That is this matrix over here. That is 0, 1, 1, 1, 0, 1, 1, 1, 0. This is called as the parity generator matrix. So what is a parity generator matrix? A parity generator matrix is a matrix whose dimension is k by n minus k. K by n minus k matrix. That means it has the number of rows will be equal to k and the number of columns will be the difference between the output bits and the input bits. The number of output bits and the number of input bits. That is the dimension of the parity generator matrix. Okay, so which means this generator matrix can be written as I3P. This is how we write it as a short form, where I3 is the identity matrix of 3 rows and 3 columns, and P is called as the parity generator matrix whose dimension is k by n minus k, whose value is given by this. This is why. So the reason why this the first portion of the output code is same as the input message is because of the presence of the identity matrix. That is the first part of the generator matrix is the identity matrix. Okay. It can either, this identity matrix that does not always have to be the first part. It can also be the last part, because here according to the definition, the first k digits or the last k digits of the output code word is the same as the message block. Here in this example, it is the first k digits. This is the first 3 digits of the output code word is the same as the message block. Okay, a systematic blocker can also be when the last 3 digits is also same as the input message, then that is also called as a systematic blocker, either the first part or the last part. Okay, so here in this example is the first part. So if it was the last part of the message was same as the code word, then the position of the identity matrix will be over here. It will be after the parity generator matrix. Okay, but here in this example, the position of the identity matrix is before the parity generator matrix. Okay, and if you look, how did I get k by n minus k? How did I get this value? Look over here. What is the value over here? What is the identity matrix of this? The identity matrix of this is k by k, right? 3 by 3, right? K by k, or 3 by 3. And what is the parity generator matrix over here? It is k by n minus k. Okay, now combine both of them. If you combine both of them, the number of rows are the same, because see, you're not multiplying, you're just simply joining them, right? So if you join them, what will happen? The number of rows will be the same, but the number of columns will increase. And what is the number of columns? How it will increase? K plus n minus k. What is k plus n minus k? Number of columns of the generator matrix. K by n minus k is equal to n, which is the dimension of the generator matrix, which is k by n. That is how we know that the dimension of the parity generator matrix must be k by n minus k, because there will be total of n columns, in which the k columns will be that of the identity matrix, and the remaining n minus k columns belongs to the parity generator matrix. That is why G is equal to I3P. This is the I3 and P are nothing but the sub matrix of G. Okay, so this is how we got the systematic block code. Okay, so which means that suppose if I'm going to multiply it, it means we know that V is equal to U into G, right? We know that V is equal to U into G. V is equal to U into G, right? So which means, or in other words, small letter v is equal to U into G, or in other words, we can say that V1, V2, V3 up to V6, okay, is equal to U1, U2, U3, U1, U2, U2, U3, and this value is 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0. What happens? So in that case, what is the value of V1 from here? Look over here. What is the value of V1? V1 is exactly this one multiplied with the first column of the identity matrix, which is equal to U1. So therefore, V1 is equal to U1. What is the value of V2? Look at the value of V2. V2 over here is, how do you find the value of V2? You multiply this with we multiply this matrix with the second column of the identity matrix, which is 0, 1, 0. So you get V2 is equal to U2. Okay, and then how do you find the value of V3? You multiply this with the third column of the identity matrix, okay, which is 0, 0, 1. So you will get V3 is equal to U3. And then how do you find the value of V4? We find the value of V4 by multiplying this row with the first column of the parity generator matrix. The first column of the parity generator matrix. The first column, which is this, or the fourth column of the output code word, or the fourth column of the generator matrix. Either this column is called as the fourth column of the generator matrix, or the first column of the parity generator matrix, 0, 1, 1, 0, 1, 1. So what you get is, so V4 is equal to U2 XOR U3, right? Exactly. And what is the value of V5? The value of V5 is, you multiply this with the second column of the parity generator matrix, and you will get U1 XOR U3. Now what is the value of V6? The value of V6 is, you multiply this with the with the third row of the parity generator matrix, or the sixth row, or the column, the third column of the parity generator matrix, or the sixth column of the generator matrix, which is 1, 1, 0, and you will get U1 XOR U2. You see, and if you look over here, the first three code words, the first three code bits is exactly same as your 3 input bits, and the remaining is where you need the calculation, and this calculation requires the parity generator matrix. For this, all you need is the identity matrix. That is how we did that is how we got the same as this structure is what you call as the systematic block code. Okay, so this is for a 6-3 block code. Now if I'm going to generalize it for an NK linear systematic block code, comma, this is how the matrix will look like. This is for an NK linear block when I'm generalizing the value of N and K. Here the value of NK is 6-3, right? That is 6-3. That is why this is called as a 6-3 block code. Now in the same example, I'm using the NK linear. So I'm generalizing the value of N and K. So if you look over here in this generator matrix, the first portion is the identity matrix and the other portion is the parity generator matrix. Okay, therefore G can be written as IKP, just like how I written over here. G is equal to I3P, just like of that. If I'm generalizing it, G is equal to IKP, where IK is the K by K identity matrix, which means IK is always a square matrix. Okay, so it's an identity matrix, and the remaining matrix, this portion, is what you call as the parity generator matrix, whose dimension is K by N minus K. You can see how it's being represented. That is, look at the first row, P11, P12, P1 N minus K. Look at the second row, P21, P22, P2 N minus K. Look at the third row, P31, P32, P3 N minus K. So this portion is what you call as the parity generator matrix of dimension K by N minus K. That is, it has K rows and N minus K columns. Okay. And just like this, how I have written the equation for V1, V2, V3, likewise generalizing it, I can also express the equations. That is, if this identity matrix is dimension is K by K, right? So up to Vk, the equation will be the same. The equation will be the same as your input message, which means V1 is equal to U1, V2 is equal to U2, V3 is equal to U3 up to Vk. Since the identity matrix dimension is K, so from Vk is equal to Uk. Okay. Now for the remaining, after the bits, after Vk bits, the remaining bits we'll be multiplying using the parity generator matrix. So therefore Vk plus 1, which is the next output code bit after Vk plus 1. How is it multiplied? We multiply the message U. We multiply the message U with the corresponding columns of the parity generator matrix. So Vk plus 1, we multiply Vk plus 1 by multiplying the message bits with the first column of the parity generator matrix. Okay, which is so you get U1 into P11, U2 into P21, U3 into P31, and it goes on up to UK into PK1. Okay, now the next word, that is Vk plus 2. Okay, the Vk plus 2. So how do you find the value of Vk plus 2? We multiply the message bits with the second column of your parity generator matrix, the second column, which is P12, P22, P32 and up to PK2. So therefore Vk plus 2 is equal to U1 P12 plus U2 P22 plus U3 P32 and goes on up to UK into PK2. Okay, this is how we get when you find the value of Vk plus, that is, we multiply the message with the second column of the parity generator matrix. Likewise, when you want to find the next bit, Vk plus 3, we multiply the message bits with the third column of the parity generator matrix, which is U1 P13 plus U2 P23 plus U3 P33 up to UK PK3. And the last code word, the last code bit, Vn, which is the last bit, right? We know it's an n bit, so it varies from V1, V2, V3 up to Vn. So the last code bit, you are finding the equation by multiplying the message bit with the last column of your parity generator matrix, or the last column of the generator matrix, which is this column over here. So you will get u1 into p1 n minus k plus u2 into p2 n minus k plus u3 into p3 n minus k, and it goes on up to uk into pk n minus k. This is how we represent the systematic block code. Okay.